Okay, this is now 4.1 part 2. So the second part of the notes on the introduction to direct proofs. And we want to, okay. So this is section 6. Whoops. Still getting used to the pen writing mechanism I have. Okay, so proving universal and proving existential statements. And we've looked at this before in the previous section, and I kind of said we'll learn later how to do this. In the previous section, we learned that we use the method of exhaustion to prove these statements. So to prove something of the form for all x, if p of x, then q of x, you must show for all x in your domain, whatever that is, let's call it D, that p of x compels the truth of q of x. Okay. So the idea with a lot of these proofs, you kind of start with this as what they call a supposition. Suppose p of x is true. Then compels just means use some sort of argument. So using algebra, axioms, common sense sometimes, and logic, show that q of x follows. So the first way we showed this previously was the method of exhaustion. Okay, but this will only work for finite sets. So if your domain in particular is some set of a number of integers, so -1, 0, 1, 2, like that, then you could go through and check x for every possible value. In general, this won't work though. And it won't work because your domain will be infinite. Okay? And by the way, there's different kinds of infinities. There's countable infinity and uncountable infinity. Things that are countable are things like the integers. Like you can count it on your fingers, or you can make a correlation between your fingers and the objects you're counting. There are things that are uncountable, so the real numbers are uncountable. That's a different kind of infinity, so to speak. There's kind of levels of infinity. So when you're dealing with an infinite set or an infinite domain, what you're going to have to do is something called a direct proof. And direct proofs are, in my opinion, the bread and butter of mathematics. We do inductive proofs, we do sort of the basic, kind of trig proofs, but direct proofs are really where it's at, in my opinion. Extremely important, always overlooked. We need these. If you're going to become a math major, you need to know how to do these. So the book tries to give you a basic way of approaching these problems. And first, what you're going to do is just reinterpret the statement in a symbolic form, kind of get rid of all the nonsense. So rewrite the statement you're trying to prove in symbolic form. Secondly, then you're going to do this thing that the book calls generalizing from a generic particular. So you're going to just suppose x is a random element from the domain. Okay, I wrote this phrase PBAC. This stands for a particular but arbitrarily chosen element. It's basically just saying it's a random element which represents every element in the domain. I sometimes call this payback. It's payback to my discrete math teacher who did not teach me one thing about proofs before I went in and became a math major and suffered for the next 4 years. Now I teach discrete math and I teach people how to do proofs, so you don't have to suffer like I did. This is my payback. Suppose X is a payback element in the domain. After we do that, we will, and it's not just an element in the domain, it's an element which satisfies P of X. So let me amend this. Okay. Suppose X is a payback element in the domain such that P of X is true. Now will come the body of the proof. And what is happening here, you're showing that Q of X follows somehow. And your hands are kind of tied behind your back when you first start these. You can't really assume anything for granted. The only thing you can do is use the axioms that are provided, your basic laws of arithmetic, like 1 plus 2 is equal to 2 plus 1. You can add things to both sides of an equation. You can use now our basic rules of logic. So if you know if this then that, and you know that this is true, you can presume that P of X is true. You could use modus ponens, modus tollens. You have to be careful though. You can't. There are some things you don't want to do, like you don't want to presume the thing that you're trying to prove and that sort of thing. They talk about that in the next section. Okay, but in general, what you're going to be using, show that Q of X follows from P of X. You use definitions, basic axioms, rules of logic, and previous established statements. So maybe you just prove something to be true. You can use that fact. And previously established truths. Right, and when you're working, you want to give a reason for each step in the body of the proof. So just like when you're doing the propositional arguments, to the side you kind of always have to put which rule you used. It's similar here. In the body of the proof, if you're doing algebra or you did some logic, you got to say, I did this because this is true. Even if it seems like it's incredibly obvious, which is hard for us because we've had so many of these axioms beat into our head, it's hard to see them as anything other than an obvious statement. And you get some teachers that get really bad that way. It's like they'll be telling you a proof and they'll be like, oh, this is obvious. Well, maybe to you, but not to us, right? You have to be kind of like that. You have to be aware that the person that you're talking to, I think maybe that's one of the reasons why they want you to write everything out. So eventually someday you could be the teacher, and you don't want to abuse your students and basically tell them, well, this is all obvious. You should already know this, when it's clear that they don't. Okay, you were taught by somebody, and you need to teach them the same way. Okay, so anyways, let's look at some problems. This first set, we want to first, we're just avoiding the body of the proof. So we'll do a rewrite symbolically, set up the first sentence of the proof, and then write the last sentence of the proof. Okay, so this is number 24 in the book. and it says for all real numbers x, if x is greater than 1, then x squared is greater than x. Right? Okay, so part A, just try to rewrite it symbolically. It doesn't have to be all symbols, but for all x in the real numbers, if x is greater than 1, then, so not too much really to rewrite here, x is greater than x. Okay, so this is, just in case I give you something that looks really, really informal, you want to make it exact. I have to do this and I have to do this. All right. The introduction to the proof should be some sort of supposition. So you always start with the word suppose. It's almost to the point where they'll give you a symbol for the word suppose that looks like this. This means suppose. Okay, but in the beginning, just write it out. So suppose x is a payback real number such that x is greater than 1. All right, so the supposition just comes from all of this stuff here. Right? Where do you want to end up? Well, you want to end up, guess what, right here. So that's hopefully going to be your conclusion. Right? Okay, so our conclusion will say something like therefore, or it follows that x squared is greater than x. And then the stuff in between generally is going to be some use of definitions. So there'll be instantiation of some variables based off the definitions. Then you'll use algebra and logic to show that this follows. In this case, we'd have to use maybe some axioms of inequalities. Let's look at another one. This is now 25. And what do we have? For all integers m and n, if m times n is equal to 1, then m equals n equals 1, or m equals n equals negative 1. Okay, so it's a part A. I'll rewrite it in some more formal way. So for all m comma n in the integers, if m times n equals 1, then m equals n equals 1, or m equals n equals negative 1. So now we go to our supposition, and again, that's from this first part all the way through the if statement. So suppose m and n are particular but arbitrarily chosen integers such that m times n is equal to 1. Sorry, the stupid pen thing. Still getting used to it. Okay. Okay. There's our supposition, and then our conclusion is the then part. So our conclusion will be then m equals n equals 1. So this part right here. Okay. So hence m equals n equals 1, or m equals n equals -1. Okay. Okay, now let's go to proofs where we actually fill out the body of the proof. So all this junk in between part B and part C we need to include. In the homework software, of course, it's just going to be fill in the blanks, and that'll give you a pretty good notion as to how these proofs go. In general, before I use the software, I would just give students as many examples of these proofs as I could, and they kind of become templates. And in that regards, they're like Mad Libs a little bit. So you have all these parts, like the A, B, and C parts, that are kind of automatically filled in, and you just have to kind of connect the dots from here to here using algebra and logic and definitions. So let's try to take a look at them, and hopefully the flavor of the proof will become apparent. And I am a firm believer that all proofs kind of have a flavor to them. And if you see enough proofs, it's no big deal. It's just there are a lot of different kind of proofs out there, and generally we at least here at the community colleges and some of the state colleges that we transfer people to generally don't have classes in proofs. If you are going to take math, it's better to have a class in proofs, but a lot of people can't get into these colleges that have proof classes. So you kind of are on your own, right? If you go to like Cleveland State or something, they've gotten better in the previous years, but my discrete math teacher was horrible. I don't know. Anyways, let's go at it, and hopefully you can appreciate the form. There's always a certain set of things that you have to do, and they all kind of look the same at the end. So if you see enough of them, you are good. All right, but like in the software, all you're doing is filling in the blanks. It's not that bad. But ideally you would do these without filling in the blanks. You do them on your own, and if you keep taking math like abstract algebra, you're going to have to do them on your own. They're not going to have like this fill in the blank stuff. Okay, they want you to think for yourself. Okay, and it really is just arguments. I mean, it's kind of like if you ever see one of those philosophy kind of things where they're arguing for this or that. That's a little bit more willy-nilly than a math argument, but it is at its base. It is what it is. Okay, I'll shut up. Let's just get it done. 29. What are we doing? The negation of any even integer is even. The negative of any even integer is even. Okay. First, I recommend rewriting it in symbol form so you can pick out the if part and the end, and then the then part. So what's the deal with this guy? It's the negative of any. So for all n in the integers, if n is even, then negative n is even. Okay, so we start with our supposition. So we suppose n is a payback integer such that n is even. Okay, so what does that tell us about this number n? Well, if you go back and look at the definition, that means that n is 2 times some other integer. And we can say that. We can bring that fact into existence. That's existential instantiation, is what the book calls that. Okay, so we use the definition to rewrite n. And our definition said that when a number is even, then it's equal to 2 times some other integer. So we note k is an integer. Right? We want to show that I gotta pause the video. Some idiot is at my door, and you know it's nothing important. There is not one person in this universe that comes to my, oh my god. Okay, welcome back. Sorry about that. My mom got locked out. Apparently I locked her out. That's her side of the story. Right, so anyways, where are we? Negation of any even integer is even for all n and z. If n is even, then negative n is even. So we're supposing n is a payback integer such that n is even. By definition of even numbers, n equals 2k, where k is an integer. Okay, we want to show that negative n. So we're sort of aiming at showing that negative n is also even. So we can use our properties of equality to finish this off, right? So you can multiply both sides of any equation by a negative. So by properties of equations or equality, we can now write, we can multiply both sides by a negative. And get negative n equals negative 2 times k. All right, our end goal is to try to show that this negative n is equal to 2 times something, right? And we could now pull that off. Negative 2k is the same as negative 1 times 2 times k. This is just the definition of a negative number. Then we can rewrite it using the commutative law, right? So 2 times negative 1 times k. So this just definition of negatives, I guess. Sometimes it's not clear what the law, where that law was first put into your memory banks, right? So I'll just make it up as I kind of go. If I don't, you probably see it. It's probably one of the axioms in the back of the book, to be honest. Here it's the commutative law of multiplication. And then finally we can multiply together the negative 1 times k. So 2 times negative k. I don't even know what that would be. Just definition of multiplication by a negative, right? See, these things are just so obvious to us by now that it's kind of hard to explain why it's true. There are some weirdnesses about that. So when I was over the break I had during the pandemic, I was reading a book on what's called axiomatic set theory. And in that context, what they do is develop addition in the context of sets. So they're able to kind of eliminate the numbers from the number system. Okay, and everything's just looked at as a set. It's weird, and they're able to define multiplication in this context. So all of these little rules that you take for granted, they can seriously, rigorously prove that they're true. And I believe that's what kind of Whitehead and Russell were doing at the beginning of the century with what their Principia Mathematica. There's more than one Principia Mathematica, but the one by Whitehead and Russell is really looking at the foundations of mathematics and make sure everything works. Anyways, now we have it, right? We have 2 times some integer. We need to state that this thing right here, this negative k, is an integer. So where negative k is an integer, because it's the product of 2 integers, negative 1 and k in particular, I won't write that. And thus, by definition of evenness, negative n is even. Okay, so that's our first introduction to a proof, a direct proof. And let's look at one more, and then we'll probably call it quits until the next video. So we'll just call this one an example. What are we trying to do? We're trying to prove that the difference of any odd and even integer is odd. Okay, so first I'll rewrite it symbolically. For all m, n in the integers, if m is odd and n is even, then the difference m minus n is odd. Okay, so the way the sort of sketch of the proof will instantiate m as an odd integer, so we'll let it equal 2k plus 1. Instantiate n as an even integer, let it equal 2k. And then we'll show that m minus n is odd via substitutions and some algebra. And then show it fulfills the definition of oddness by showing that it's 2 times some integer plus 1, and therefore it follows. Okay, so let's get at it, do our suppositions. So suppose m and n are payback integers such that m is odd and n is even. Okay. Some teachers will actually then have you write down where you want to end up at the bottom. So you could write, therefore, m minus n is odd, if that helps. Sometimes having a goal in mind will help you. Okay. All right. So anyways, so where are we? Suppose m and n are payback integers such that m is odd and n is even. By definition, of even and oddness, we note m is equal to 2 times k plus 1, and then n is equal to 2 times k, sort of. Okay, so there's one issue here. We want m and n to be any even and odd numbers. The way I have it written, these two m and n numbers are connected. So if m is equal to 7, then n has to equal 6 in this case. So it doesn't really represent particular but arbitrarily chosen integers. So to get around that, you need to say that these guys could potentially be different. In other words, call one k1 and the other one k2. All right. Okay, now we're going to consider that difference. So we're trying to show that the difference is odd. Okay, so first we'll do a substitution. So m is 2k1 plus 1, and then n is 2k2. And we should be putting these, and we could put these in parentheses. That may be a little bit better. I don't think I used parentheses here because I was already using parentheses over here. Okay. Okay, so next consider this fact. We can rewrite this using the commutator law of addition. So this would be 2k1 minus 2k2 plus 1. Hopefully you see where I'm going with this. I need to show it's equal to 2 times some integer plus 1. Okay. And then I can factor out the 2. Which is the reverse of distribution. And then I got it, right? I just have to show that this thing is an integer. So I'll say okay, so k1 minus k2 is a difference of integers, and the integers are closed under subtraction, so therefore that's an integer, and we got it. Hence, m minus n is 2 times some integer plus 1. And is therefore odd by definition. Okay, so we'll leave it at that, and in the next video we'll talk about common mistakes. Thanks for watching. Let's go tell my mom I'm sorry for locking her out. Ugh.